going to prove an identity for all values except the non-permissible values. And so let's start off by actually finding those NPVs. So the NPVs usually come from either the square root of a negative or, like in this case, a possible denominator of 0, right? So let's find those non-permissible values for this particular identity. So they would come from either denominator being 0, right? So for the first one, if sine cubed of x is equal to 0, if we take the cube root of both sides, that means that sine of x has to be 0. And so that means that x must be the inverse sine of 0. And over all values from negative infinity to positive infinity, that means that x can be anything of the form sine is our y-coordinate on the unit circle. So that's 0 plus pi k. So that's pi k for any integer value of k, like so. And the other option is if this denominator is 0, right? So the NPVs would be this set of values, or if 1 plus cos x happens to be equal to 0. So another set of non-permissible values would come from this equation, right, if that denominator is 0. And so that means that cos of x would be -1, which means x would be the inverse cos of -1. And for all values, right, x would be of the form, that's the x coordinate for cos, and so that's at pi. So pi plus 2 pi k for any integer value of k. And you'll notice that this set of values is a proper subset of this set of values, right? This means that every value in here is properly embedded inside of that set of values, right? And so we really only need to consider this first set of values. This is kind of redundant. And so this is really our set of NPVs, okay? That just means that when we actually plug in values inside of our identity, this is always going to work except for the ones that make the whole thing go awry, let's say, okay? So now let's actually go ahead and algebraically prove it. I'm going to leave the right-hand side the way that it is, and we're going to manipulate the left-hand side to make it become the right-hand side. So first things first, in the numerator, we have tan of x. I'm going to write that as sine or cos. So we'll have sine x over cos x minus sine x over, again, sine cubed x, right? I like writing my tans and my cotans if they were there in terms of sine and cos. Now, in the numerator, we're having a fraction minus a non-fractional term, let's say. To combine them together, we need a common denominator. So to get our common denominator, let's multiply this by cos x over cos x, right, to get our common denominator. And now we'll have sine x minus sine x cos x all over cos x all over sine cubed x, right? And now we have a fraction divided by sine cubed x. Whenever these things happen, this is akin to saying, I don't know, 1/2 divided by 3. What's half of a pizza divided into 3 pieces? Well, that's just the 6th, right? So we multiply the two denominators. That's an easy example, but the same applies here with these two denominators. And so this left-hand side now is written as, whoopsies, minus, sine x cos x, right? And our denominator is going to be the product of these two denominators, right? And so we'll have all over sine cubed x cos x, right? Now, we can factor sine x out of both terms in the numerator. And so that will, we can factor a sine x out of both terms, or we can say, well, there's a sine x factor in every single term, and so we can cancel it out. So the cube is going to become a squared factor down in the bottom. This cancels out, and that cancels out. And so now our our numerator reads 1 minus cos x all over sine squared x cos x. And where do we go from there? Is a good question. We could here's what we'll do. I'm going to write sine squared x as, using our Pythagorean identity that sine squared plus cos squared is equal to 1, I'm going to rewrite sine squared x as 1 minus cos squared x, okay? And I'm going to note that this is a difference of squares. So, right, we have 1 squared minus cos squared x. That is a difference of squares, right? Meaning that it can be factored as a difference of squares as 1 minus cos x times 1 plus cos x, right? And so that sine squared x, we're going to write as the product of these two factors. And so now we are down at 1 minus cos x all over 1 minus cos x times 1 plus cos x, still times the cos x embedded inside the denominator, right? And now you can probably see a 1 minus cos x factor completely canceling out. And so that brings us down to, hopefully you can still see, 1 in the numerator, and in the denominator, we'll have cos x times 1 plus cos x in brackets from the term, from the factor in the previous step. And now you might notice that this is 1 over cos x times that second factor. 1 over cos x, that is secant x, right? 1 over cos x is itself secant x. And so that means that we can write this as secant x, excuse me, that becomes secant x over the remaining factor in the denominator. That's 1 plus cos x. And that is exactly what we wanted to get to. And so there we go. This here proves that our identity is in fact an identity for all values except our NPVs. And so again, just a quick recap, the idea is just to kind of do the next step that is in front of you. Take what the identity gives you. When we have tan, we can write tan in terms of sine and cos. When we have fraction and subtraction or addition, we know we can get a common denominator and then combine them with that common denominator. Then we can start factoring, combining denominators. We can be creative with our use of identities, right? Those Pythagorean identities are really, really useful, and we often have to use them in creative ways to kind of get what we need out of our expressions, right? Factoring a difference of squares, canceling out a factor, and then writing it the way that we need to write it in the end. This is just one more example that can hopefully help you become really good at these identity proofs. So I hope this helps, and thanks for watching.